Okay, Bismillahirrahmanirrahim. We are going to start with the second semester of your BS and MSc program. And in second semester of this mathematical methods course, mathematical method course consists of the following 5 chapters. Because of the time constraint and this COVID-19 problem, we may not be able to complete all of them, but we'll try our best to do little portion from everyone. Now, first is differential equation in physics, and that is chapter 12 in your that advanced mathematics book by Murray or Spiegel, Shyam series. Then second is special function. This is chapter 10 and 11. Third is Fourier series, chapter 7. 4 is integral transform, chapter 8 and chapter 4. 5 is boundary value problem and Green's functions. And this is all of the course. So what I have decided, I'll start with the integral transform. That is chapter 4 because it is relatively easy, and the first two are relatively difficult. This is also easy. That is difficult. Maybe we're not able to touch even that. Anyway, we are going to start with integral transform. Now, as is obvious from the name, transform, it means that something has been transformed to some other thing. Now, integral transform means that you are transforming a given function. I am emphasizing that we are transforming a given function ft. This is given to us, and people ask us, transform ft into a function of new variable g alpha. So g alpha is a new function, ft is the given function, and k alpha t is known as kernel function. Kernel function. Now this kernel is not army kernel, it is kernel means the central important portion. So this is important function, helping function, which helps to transform this into that one. And this kernel function is function of two variables, alpha and t, and look, this is only t and this is only alpha. So it separates the alpha portion from t portion. But this is the general form of integral transform. Now, what I have written here, these are the special cases. And look here, I am saying if k alpha t, that is k alpha t, if you take it equal to e raised to minus alpha t, okay, so k alpha t is e raised to minus alpha t, a tending to 0, b tending to infinity. See, value of a is tending to 0 and value of b is tending to infinity, then this expression reduces to g alpha, because a is tending to 0, b is tending to infinity, is integral 0 to infinity, ft e raised to minus alpha t, because you have substituted k alpha t as e raised to minus alpha t dt. So that is known as, wherever you see this type of transformation, where there is a negative exponential function of two variables, any two variables, then that, and here is a function fx or fy or whatever it is, then this is known as Laplace transform of ft by the function e raised to minus alpha t. It means ft is being transformed into g alpha with the help of e raised to minus alpha t, and this type of transformation is known as Laplace transform. This we'll be studying in detail, and we'll be solving some differential equation with the help of that. Then second case is if k alpha t, that is the same kernel function, if you take it as t raised per alpha minus 1 and a is tending towards 0, b is tending towards infinity, then this thing takes the following form: g alpha is 0 to infinity ft t raised per minus alpha minus 1 dt. It means ft is being transformed to g alpha with the help of a new kernel function t raised to alpha minus 1. So the transformation will be different, and that is known as Mellon transform of ft, because this Laplace did it and this Mellon did it. Both were mathematicians. The important one is Fourier transform of ft, which is given by g alpha is equal to that. Now I haven't said by put this equal to that. It is obvious k alpha t is e raised to minus I alpha t, a tending to 0, b tending to infinity, ft is transformed to g alpha. This is just normalization constant. If you don't put it even, then it is Fourier transform of ft into g alpha with the help of e raised to minus I alpha t, and that is the normalization constant. Then from here, if you put this as cosine alpha t minus I sine alpha t, then separating the real and imaginary part, we come across with g c alpha. C mean cosine transform. So this is function ft being transformed to g alpha with the help of cosine alpha t. This is also a Fourier transformation, but it is known as Fourier cosine transform. And similarly, this is known as Fourier sine transform, where your kernel function is sine alpha t, a tending to 0 and b tending to infinity. So we'll be studying, in fact, two of them, Laplace transform and then use of Laplace transform in solving the differential equation, and we will be studying also this Fourier transformation. The other transformation are not in our course, so we won't touch them. Okay, so this was a general discussion by of the integral transform. Now we come to, first of all, Fourier transformation. Now Fourier transformation are given by this equation number, let me call it 4, and that is 5, and that is 6. Okay, now 4 is the Fourier transformation, and okay, now let me write something here now, because now we are going to discuss in detail the Fourier transformation. And I told you that Fourier transformation is given by equation number 4. Now what I am going to now, here we were talking about variable t. Now I am going to write the Fourier transformation fx is equal to minus infinity to plus infinity fk e raised per I kx dx, or sorry, this is dk, and similarly fk is equal to minus infinity to plus infinity fx this is minus, by the way, e raised to ikx dx. This is 7 and that is 8. These two transformations which I have written, these are the Fourier transformation. You can see here there is no normalization constant, but you can put it there, you can put it 1 over 2 pi, but these are the general form. Now look, this is very important to see. Here, look here. Somebody says fx given to us, transform fx into a new function fk with the help of kernel function e raised per ikx. Okay, so minus infinity to plus infinity as we do in the Fourier transform. There I took it as 0 to infinity. Now I am taking to minus infinity to plus infinity. Okay, so look at the thing. Fx e raised per ikx dx. That is the transformation of the function fx into fk. And if you look here, look at the sign, both are opposite sign. It is the transformation of fk into fx. And through that type of integration, here variable is k, here variable is x. Now, this is known as inverse transform of this, and this is known as inverse transform of that. In one case, fx is given, and you are going to calculate fk. In the second case, you are fk is given, and you are going to find fx. Okay, so this is how this thing is done. Now, what I can do, I can take this fk, starting with that, I am going to write it, and I am going to write it 1 over 2 pi square root, that is the normalization constant, you know, which you if you put it there or if you don't put it there, okay? So, but usually it is there, 1 over 2 pi square root. Now, look at that. That is the same for the two, okay? Now it's up to you if you put it there or you don't put it there. So I have put it there because, you know, in mathematics it will be always multiplying with that, but its actual thing is this one where you are going to transform. So fk is equal to 1 over 2 pi square root minus infinity to plus infinity fx, and then I am writing this as cosine kx plus I sine kx. This much you know from the trigonometric relationship into dx. Okay, here it is, sorry, I'm sorry, make it correction. It is fk, it is dx, and it is, sorry, this is fk, it is dx, and that is dk. Okay. So this is what I have done. I have separated open form. Okay. So this is equal to 2 over 2 pi square root 0 to infinity fx cosine kx dx plus I over 2 pi minus infinity to plus infinity fx sine kx. Now, how I have done it? I have done it under the condition that I am assuming that fx is an even function of x. fx is an even function of x. Let me define them. A function fx is said to be even, that is, if you replace x by minus x, you get the same function, then fx is even. And if on the other hand you replace x by minus x, you get minus fx, then fx is said to be odd function. Okay? So what I have done, I am assuming that fx is equal to f of minus x, that is fx is even. Fx is even. Okay? Then what happens? If you separate these two, because this will be multiplied with this and with that, this is what I have done. But since fx is even, this is even, cosine kx is also even, because cosine of minus kx will be same as cosine kx. So this is even, that is even. So even into even is even, and in that case you can write it as 0 to 2 times the same limit, that is like this. Okay? But here in this case fx is even, but this is odd because you replace x by minus x. What you get? Minus sine kx. So this is odd function. And whenever that is the situation, this integral is always 0. Because, okay, so let me write it here. Some limit, let's say a minus a to plus a, fx dx, and if this is even, then you can write it as 2 times 0 to a fx dx. On the other hand, if this is odd, then this result will be 0. This property I have used here. So if fx is even, then your fk, you see this 2 can be cancelled with that, with the square root, and you will be having 2 over pi square root, 0 to infinity, alright, and you have fx cosine kx dx. This is the so-called Fourier cosine transform of fx, which I have written here. Similarly, in a similar way, you can say, that if you say, if fx is odd, that is f of minus x is equal to minus fx, then look, put here in the same expression, what you get, look, this is odd, this is even, so even into odd is odd, and this result will be 0. You cannot write it as 0 to infinity like that, so that will be 0. However, this is odd, this is also odd, and hence this can be written as 2 times, so I can write this expression as fk is equal to 0 plus 2 times I 2 pi square root 0 to infinity fx sine kx dx. Remember, fx is odd function, this is odd, hence I have written it as a 2 times 0 to infinity, and that's it. And this is further, if you remove I, what you get, 2 over pi square root 0 to infinity fx sine of kx dx fk, that is known as Fourier sine transform. So what we have done, we have defined Fourier transformation, and from Fourier transformation we have defined Fourier cosine transform and Fourier sine transform under the condition that if fx is even, then you get Fourier cosine transform, and if fx is odd, then you get Fourier sine transform. Okay, so that is one thing. Now let me take an example. Time sumra shevede. Sadi bas khatmo lik saatte bas. Biya dei sabak bamai kana. This is exercise problem 8.15a, page 208, Advanced Mathematics. Find Fourier transform of fx is equal to 1 over 2 epsilon, and x positive or negative is less than epsilon and is equal to 0, x positive and negative greater than epsilon. So that is the situation with us. That is the problem. Says that find Fourier transform of this function. The first thing you have to do in all these problems, plot the graph. Graph will be look like that. This is x. This is fx. Okay, this is x is equal to 1 over 2 epsilon, and that is x is equal to minus 1 over 2 epsilon. Now he is saying that value of x, whether positive or negative, is 1 over 2 epsilon. So in between this, the value is 1 over 2 epsilon. That is fx. Okay? And outside this, when it is greater than epsilon, this should be epsilon and this should be minus epsilon. So what it says, that value of x between epsilon and minus epsilon, fx is 1 over 2 epsilon. Okay? And when it is greater than epsilon with positive or negative sign, then it is 0. So this is 0 on this side, 0 on this side, and in between that, so you have just one pulse of a wave. Now how to find its transformation? We know that fk is equal to 1 over 2 pi square root normalization constant minus infinity to plus infinity, but I am not writing it, and this is equal to 1 over 2 epsilon e raised to I kx dx. Now look what I have done. This is your fx, this is your helping function e raised to I kx, that is dx. Limit is, because from minus infinity to minus epsilon it is 0, from epsilon to plus infinity it is 0, there is no need to write it. So it starts with minus epsilon to plus epsilon, and that's the normalization constant. This is what you will integrate, and look, if I integrate, this can be taken out, 1 over 2 pi epsilon, 2 pi square root, 1 over 2 epsilon outside, integral of e raised to I k x dx. Let's integrate 1 over 2 pi square root 1 over 2 epsilon. Integral will be e raised to I k x divided by I k minus epsilon to plus epsilon. This is further equal to 1 over 2 pi square root into 1 over 2 epsilon k, and inside it will be e raised to I k at k epsilon, you put this limit, minus e raised to minus I k epsilon, you put this limit, divided by I, which is already there. Take this 2 inside and see this is equal to 1 over 2 pi square root. What is this? Sine k epsilon divided by k epsilon, which is this. So this is the Fourier transformation of fx into this one. On this side there are only k, no x, so x is eliminated. Now you have the Fourier transformation of fx into fk. So I'm going to stop here. You just go and study the book, chapter number 7. Details are given in there. Try to attempt the question. If you have some questions, you can talk me on telephone through message, not direct call. Write your name and say what I want to talk you. I have problem, then I'll give you a call myself at a proper time, okay? So I won't accept any call without identification. Okay, thank you very much.